Okay, so the second part of our velocity analysis in chapter 6 is going to be looking specifically at relative velocities. So relative velocities using the graphical method is going to be a method that we're going to be using, a process that we're going to be using when we need to know the velocity of something that is dependent on something else that's in our linkage. So up until this point, the first part of chapter 6 was looking at a single link and the relationship between the angular velocity on it and the straight line velocity on any point along that link, depending on how far it was from the center of rotation. But now relative velocity method is looking at when we have a couple different links together in a mechanism, a 4-bar mechanism specifically, how we can determine velocities of elements that are dependent on rotations or positions of other linkages, okay? So the base equation that we're going to be looking at is this equation down here. And in its very generic form, okay, we'll relate it to the diagrams that we have, but we're going to be looking for instance, the velocity of something that is unknown. Like we need to find this straight line velocity is going to be equal to the velocity of something that's known, meaning magnitude and direction. We know everything about it, plus vectorially the unknown velocity relative to the known. Okay, so this doesn't mean a whole lot to us, but when we look at it in terms of a 4-bar mechanism, we'll put some letters and things in there and it'll start to kind of come together. We also need to remember that if we need to find an angular velocity, for instance, if we have an oscillating link, and we need to know what its angular velocity is, we're going to need to determine what a straight line velocity is on that link and then how far away from it is. So we're going to be using that equation again in that W is equal to V over R, or V is equal to W times R, depending on which we're going to be looking at. Now, as we look on points of a link that are limited to pure rotation or pure translation. So what this means is we need to determine the path of the point that we're trying to find the velocity on. So for instance, I'm actually going to go to our handout right away here. I'm going to go underneath my camera. And when we look at a 4-bar mechanism, let me make this as big as the screen. Like we see here, so I'm on page 7 where we had left off. When we look at a 4-bar mechanism, and we look in terms of link number 2 and link number 4. Those are the 2 links in a 4-bar mechanism that are only going to rotate around a fixed center, okay? The other type of 4-bar mechanism that we have on the opposite page here is going to be a slider crank. And that means that our slider can only go translationally, okay, or in a straight line. And then the crank can go rotationally around that fixed center, okay? So when we're trying to determine what velocity we're trying to find, we need to know, is it on a link that is rotating about a fixed center, or is it on a link or a slider like we see here that is going to be translating in only a straight line, up, down, left, right, whatever it might be, okay? And once we determine that, then it starts to clear up the path that we're going to take to find those velocities, okay? So in terms of a slider crank, first, before we go back to the other one, if we know, and most often we do, we usually know what's going on the crank here, like how fast that is rotating around based on maybe a motor that is driving this mechanism. And then we want to know, okay, with this length and that length of our connecting rod, how fast is this going? And this slider is dependent on what's going on the driver, okay? That's why we need to use relative velocity. These two aren't directly connected. They're connected through the connecting rod. So we need to use this relative velocity method to get at it, okay? Now, additionally, if we look back at the other one, this one is a 4-bar mechanism with a crank and then an oscillator or a rocker on the output. So here we've got two links that are going to be rotating about a fixed center. So if we need to find out how fast this is going back and forth, or what its angular velocity is, we need to find the straight line velocity, in this case, on one of the points on that link, which would be C, but this is all dependent on what's going on over here on the crank. Okay, so again, relative velocity method, but we've got two different types of mechanisms in the end, crank rocker or crank slider, but identifying what is the type of motion or velocity that we're looking for based on what type of a link that point is on. Okay, so when we are using when we want to determine the velocity of a point that relies on another, we're going to be going through this process. Number one, we will always create our kinematic diagram. Okay, kinematic diagram comes first, and the kinematic diagram is going to include all of the standard symbols for frames, for instance, the standard labels for each one of our links and each one of our joints, and then also any known values like rotational motion that we are either given or we want to find. Okay, so we're going to start with our diagram. Then what we're going to do is we're going to determine what we need to find. So depending on the problem, all right, this might be a known value. Okay, so let's say this is equal to 100 RPMs, for instance. Our W2 is 100 RPMs going in a clockwise direction. And we want to find, okay, the output, if this is our input, what is our output? Our output, a very common problem that we would want to determine, is what is the angular velocity of link number 4? Okay, what is the motion? What is the rotational speed of link number 4 at this instant when link number 2 is rotating clockwise at 100 RPMs? Okay, first of all, you would probably, kind of move this around and think, okay, W4 is probably also going clockwise at this moment in time. Okay, so that's part of it. But to determine how fast it's going, you see how it's connected through here? So it's not a direct, we can't go from here to here and say, oh, it's 100 RPMs. It's not. It's not. So what we're going to have to do is we're going to have to use this relative velocity method. Now, the relative velocity method is going to be this equation down here. Okay. Now, this equation down here, now we're giving it letters. In its initial form, very generic form. Actually, I want to go to the one that I had in the book. I think it was better to look at back here. We go to this slide right here. It says the velocity of the unknown is going to be equal to the velocity of the known plus vectorially unknown relative to the known. Okay, so in our problem underneath our camera here, we now have C. Okay, we want to know what the velocity of C is because C is on the same link that we need to know the angular velocity for. Okay, and it is going to be directly related relatively to and connected to velocity of B. Okay, now velocity of C, as we look here, if we look at it just on a single link, and we know that this link is going to be rotating in a clockwise direction, what is going to be the direction of the straight line velocity of point C? Perpendicular to the link or the radius back to where it's rotating around, right? To its center of rotation, perpendicular. And because this is going in a clockwise direction, this is going to go up and to the right, correct? We would expect that, right? So we would call this VC. VC. Okay, great. So now as we look here, we know what its direction is, but we don't know what its magnitude is. Because remember, every one of these vectors needs two quantities, magnitude and direction. We don't know what its number is, but we do know which way it's going. Okay, for sure. Now equal to, now this is our unknown value in that generic equation. That's the unknown value. We don't know anything about it. Now let's look at point B. Point B is over here. And we know that point B is on a link that is rotating at 100 RPMs, right? Now, how long do we want link number 2 to be? How long do we want this radius to be? Tell me. 5 inches. 5 inches. Okay. So we know how long that link is. We know direction it's rotating in, and we know how fast it's rotating, W, right? So even though we don't know the number yet, but we know we can calculate the velocity of B right here, knowing the angular velocity of the link that it's on and how far away from its center of rotation it is, okay? So this is going to be step number 2. What is the magnitude of velocity number 2, which is going to be our known value, okay? Now, as we look here, W2 is 100 RPMs. Can we put that number in there? No. What do we need to do first? We need to convert it to radians per second, our favorite, right? Okay, so before we put it in here, this 100 RPMs need to be converted to something in radians per second, okay? So let's go ahead and do that, because I think one of the best ways to kind of figure out a process is to do it. So I don't have a whole lot of room here, so I'm gonna go down at the bottom of my page here, and we're gonna put it down here. We're gonna say 100 revolutions per minute. Okay, and we are going to do that conversion. Remember, when we do RPMs, we want to expand it out, put revolutions on top, minutes on the bottom. And we know that in 1 revolution, there's 2 pi radians. So revolution go on the bottom so that we can cancel. And 2 pi radians goes on top. And then we need minutes into seconds. So since minutes is on the bottom here, it's going to go on the top here, 1 minute. 60 seconds. So minutes cancel and I'm in radians per second. What's my number for my W2 then? What's my number and units of radians per second? .472. Yeah, that looks good. Okay, that's the number now that I'm going to put up in my equation. So if I go up here and I say, okay, VB is equal to 10.472 radians per second times the radius of 5 inches. Okay. I now know the magnitude of velocity B. Do you get 52.355? And what are my units here? Inches per second. Yes, inches per second. Remember, radians are unitless. And if they're multiplied by anything, they just drop out. They magically disappear, right? So it's inches per second is going to be what our velocity, which is exactly what we're expecting, right? Distance over time, distance over time. All right, so now this is the magnitude of B. So we can say we know magnitude of B, right? Do we know what's B's direction? Yeah, we do. Yeah, we do. Which way is B going? The link is going clockwise. Which way is VB going? VB is going to be in a straight line. Yep, perpendicular to the radius back to the center of rotation. So this is going to be a 90-degree angle. And because this is going in a clockwise direction, it's going down and to the right. Velocity of B. And its magnitude is 52.355. You see that? So good. All right. Now, I know direction. So magnitude and direction for each one of those. So those check marks, magnitude, direction for each one. Let's look at the velocity of C relative to B. Now, this is a new one to us, right? This is a new one. These two, we were looking at the last time we were together on single links that were rotating about a fixed center, the relationship of the straight line velocity, always perpendicular to the radius back to the center of rotation, and it's going to be in the direction of rotation. So those two we knew. But now we've got the relative velocity. So the velocity of C relative to B is going to be perpendicular to the line connecting those two. the line connecting those two. So if this line right here is horizontal, the direction of the velocity of C relative to B is going to be either up or down. We really don't know, but we know that it's going to be perpendicular to the line or the link connecting C and B. C and B, that's between them. So this is going to be our velocity of C relative to B direction wise. So as we look here at these lines that we just sketched in here, think about CAD, right? Think about CAD. I need to draw my diagram to scale at the right angles. So now I can use CAD to put these values in, or these directions in perpendicular to, and when I know magnitude, I can draw them to length, right? And I can get nice, accurate graphical results. So we'll be using the CAD for exactly that. So that's why, number one, you're always going to draw your diagram to scale in CAD. And then number two, when we get our velocities going, we want to get our directions off of that diagram as well. So drawing lines perpendicular to different lengths is going to be important, and then putting their velocities at their locations. Okay. Now, as we look at this equation, we know that we don't know magnitude here, but we do know direction. So if I have a vector equation, chapter 3 stuff, remember, we could have two unknowns in any given vector equation, as long as we had one unknown on one side of the equation on the equal sign and one on the other, which we do. The equal sign separates each one of these two unknowns. So that means that we can proceed with creating this vector diagram and using it to solve for the unknown magnitudes, just like we did back in chapter 3. Okay, just like we did it back in chapter 3. That was why we practiced there. So the next thing we would want to do is we would want to draw the vector diagram. So we'll call this step number 3, and these two kind of go together. Okay. So I think if I draw, let me just look. 1, 2, 3. Okay. So I'm going to start this right about here. Okay. Here's my origin. As you know, you always need to start your vector equations with an origin, and the origin is going to be, I like to say, the equal sign. So as I look at my equal sign, I want to start on the side that I know the most. And you'll notice that on the right-hand side of my equation, I know the most right here with VB. So I'm starting there. I know VB's magnitude, 52.355 inches per second, and I know its direction. I know it's going to be going down and to the right. So we're going to sketch here. This is process. We're going to sketch a vector that is going to be velocity B. The length of this represents the 52.355, and the direction comes from being perpendicular to that link. Okay. Now, on the endpoint of VB, we're going to start the tail, if you would, and we're going to add vector C relative to B. Now, we don't know the magnitude or in which direction, I mean, up or down, that this is going, but we know its line of action is going to be perpendicular to link number 3. So on the endpoint of VB, we're simply going to draw kind of a line of infinity, and this is going to represent the velocity of C relative to B. We don't know if it's going really, up or down, but we're just going to draw it. Okay, line of action. Then that completes everything that we can do on the right-hand side of the equation. We're now going to cross over, go to the left-hand side, and we're going to go to VC. Now, VC, we know, is going line of action up and to the right. We don't know how long this is yet. Okay, we don't know how long that is. So we're going to take that line of action and we're going to go back over the equal sign. So we have to start back at our origin. And now we're going to draw a line through there along that same line of action. And we'll find an intersection. All right, you see, I see head shaking. Yeah, now I see it, right? You see what we have here. So now we need to add our arrowheads, but we have to look back up at our equation here to make sure we know what we're doing. So on the end of VB, we know that we're adding the velocity of C relative to B. So the tail of VCB is going to start there, and its tip is going to go to the intersection. Okay, so this is going in an upward direction. And then when we look at the velocity of C, we start back at the origin. Its tail is going to start here, and its tip is going to go to the tip of that last vector. So this is going to be velocity of c. Now we're drawing this in CAD. We're pretending we're drawing this in CAD. So how are we going to get the magnitude of VC at this point? Just going to simply measure it, right? Yeah, just like we did in chapter 3. So we're going to measure along here and we're going to get the actual dimension. Okay, that's going to be the magnitude of the velocity of c. Okay, velocity of c. And what would the units be here? Inches per second. Remember, velocity of v was in inches per second. So all of those vectors are going to have the same units. Okay, now remember, our ultimate goal was not VC. Our ultimate goal was, what is the rotational speed of link number 4? So the rotational speed of link number 4 is going to be our step number 4. Okay, step number 4. How do I calculate the magnitude of a W4? Remember the base equation here? If I take this and I solve for W, it's going to be W is equal to velocity divided by radius. So in this case, I'm going to have W4 is equal to the velocity divided by radius. Now, which velocity? C, right? And then the length, we have to figure out a length yet. We didn't fill that in. So my velocity is going to be the velocity of c, and I don't know what that number is right now, but I do know it's in inches per second, divided by, what do we want our radius to be here? If this is 5, this is, what do you think? Proportionally, what do we see? Maybe 4-ish, right? Okay, so this would be divided by 4 inches. Now let me write it nicely. Okay, so now we're again process. Okay, units. Notice that my inches cancel out and I'm left with nothing per second. Or is it nothing per second? Radians per second. They all of a sudden happen. They magically appear, right? They're like Lucky Charms. Okay, so it's going to be actually whatever our number is, our units are going to be radians per second, right? Radians per second. That's going to be our W4. Now, we will not leave our final answer in radians per second, right? If we're ever asked to find out what the final angular velocity is of a link, our answer will come out of that equation in radians per second, but then what will we do? We will actually convert it to RPMs, revolutions per minute. Sorry, this from before. Yeah. Okay. So step number 1, diagram. Step number 2 is we're going to calculate velocities that we know so that we can use them in step number 3 for our velocity equation, which then will dictate how we're going to draw that velocity equation, right? The vector diagram, I should say. Then once we have this velocity, we can then plug it in to calculate, in this case, the rotational speed of that link that we're interested in. Okay. Any questions on the process? Is that kind of easy to follow or to see how we would work through that? Graphical solutions only. All right. So we're going to be using CAD again. This is going to be kind of critical. All right. Now I tried to pick problems that you guys are going to do that you've already drawn in previous illustrations. So you'll kind of see some familiar mechanisms that we've been looking at. Okay. So if you save those files, it should be helpful in not having to like recreate the wheel, each and every time. There might be 1 or 2 though that you will have to do new, but I think a couple of them are going to be repeats. Okay. So let's look at another process. And this one is going to be of a slider crank. Okay. Now here, this is going to be a very similar process, but in the end, the final answer that we get is going to be a little bit different. So for instance, on a slider crank, we know that our slider can only go in this case, a horizontal direction. It's only going to be in a straight line. So the velocity at point C is either going to be left or right. Okay. It is not going to be on a rotating link. So once we find velocity C of the slider, that's it. All right. We don't have to then put it into a W equation. Okay. Only when we have oscillating links do we have to do that. So here, when we know what our W2 is, we'll say that this is 200 RPMs. Our length of link number 2, how long do we want this one to be? Did somebody say 3? 3 inches? Yep, 3 inches. Okay. How long do we want our connecting rod to be? 5. I heard 5. Okay. 5 inches. Okay, good. 5. So we want to find out what is the velocity at C. Now, as we're looking here, you'll notice that the rotational direction of W2 is going to be in a clockwise direction. So what does that mean for the velocity at C? Is it going to go left or is it going to go right at this instant in time? To the right. Yeah, exactly. So velocity of C is going to be like that, right? Also, there's a velocity, a straight line velocity at point B, right? On that rotating link. What direction is it going in? Up and to the right, and it's going to be perpendicular, right? Perpendicular to, oopsies, B. It's going to be perpendicular to that radius back to its center of rotation, or link number 2 in this case. There's one more velocity on here that I'm not showing yet. What's the third velocity that I need to add? The velocity of the velocity of C relative to B, right? And that is going to be perpendicular to the link connecting those 2 points. So the velocity of C relative to B is going to be along this line right here, perpendicular to the line connecting those 2 points. Okay, the line connecting those 2 points. Now, when we draw our vector diagram, in this case, we're going to say that our unknown velocity, which is going to be C, that's going to be the end result of our input over here on the crank, it's going to be equal to the velocity of B plus vectorially C relative to B. Okay. Now, as we look at the velocity of B, well, no, we should start at C. As we look at the velocity of C, do we know its magnitude in this problem? No. Do we know its direction? Yeah. So we can put a check mark for that. What about for B? Do we know B's magnitude? Not yet, but we know everything about link number 2 that we could calculate it, don't we? We know its length, so we know its radius, and we know its rotational speed, the W2. So we can get it. So we know, we can say, yeah, we know the velocity, or we know the magnitude / we can calculate it. And we also know the direction. We have it up here, right? It's perpendicular to link number 2 going in the direction of rotation up and to the right. Velocity of C relative to B. Do we know magnitude here? No. But do we know direction? Yeah. We do know direction. We know that it's perpendicular to that link connecting the 2. So you'll notice that we again have 2 unknowns in this one equation, which is fine for a vector equation. And we have each one of those unknowns separated by the equal sign. There's one on one side, one on the other, right? So we can solve for that. So let's first calculate the magnitude of velocity at B right here. Okay. And then we're going to do our sketch of our vector equation one more time before we get into using some AutoCAD. Okay. So velocity of B, I'm going to use some space down here. So my velocity of B is going to be equal to W2, which is the length that it's on, times radius number 2. Now, W2, given in the problem, says that it's 200 RPMs. We can't use that. We need to convert that to radians per second. So I don't have a lot of room down here, and I know I got to get a vector equation in. So I'm going to do my conversion up over here. I'm going to say 200 revolutions per minute. Convert that to radians per second. 1 revolution here, 2 pi radians. Okay. And then 1 minute on top, 60 seconds on the bottom. Revolutions and minutes cancel out. We're left with radians per second here. So my W2 You guys get 20.94 radians per second. Okay. So that's going to be the number that we use down here for our W2. Okay. So 20.94 radians per second times the length of that link, which we said was 3 inches. So 3 inches. So our VB then (62.83 inches per second). Radians like disappear, right? Because when they're multiplied by something else, then the something else is the value. Okay. Virtually, guys, you doing okay? Make sense? Okay, cool. So now this is the magnitude, whoopsie, MAG, magnitude of that velocity. And now we are ready to start our vector diagram. So as we look up here, just to kind of figure out where our origin is going to be, we've got VB going up and to the right. We've got this and we've got this. So, okay, I think we can put our origin right about here at, maybe a little bit lower. Hold on, I'm going to go a little bit lower. Right about here. Okay. And that's going to represent our equal sign. So we're going to start with our velocity at B. We know magnitude and direction. So we know that magnitude is 62.83. And we know it's going up and to the right, right? So this is going to be our VB. Now, on the vector diagram, when you draw it, it's going to be really just like when you did it for chapter 3. On the vector diagram, don't worry about adding every dimension and every angle for all of the vectors. Just worry about your final resultant. That's it, okay? And what you're finding. But make sure you do the labeling. So call this VB, so I know that that's it, okay? Make sure that you put an origin. And I'll be demonstrating this tonight in CAD as well. So you'll see a good representation of what we're looking for. Now on the endpoint of VB, continuing on the right-hand side here, we're now going to put the line of action of V C relative to B, the velocity of C relative to B. So we're going to put right on the endpoint here, something right about like that. So this is going to be VC relative to B. Now we've exhausted everything on the right-hand side. So we're going to go back to the left-hand side. So starting at our origin, we're now going to draw the line of action for velocity at C, which is going to be horizontal. Okay. So adding our arrowheads, tip to tail from VB plus VC relative to B. And then VC starts its tail at the origin and the tip goes to that last vector on the right-hand side. So this is going to be my VC. And to find that magnitude, we will simply measure it, right? We're going to measure it. Now, because this is a slider, we just wanted to know how fast and in what direction was that slider going at this instant in time. We're done. C does not rotate, so we're not going to be worried about an angular velocity for point C. It's only going in a straight line velocity to the right at whatever we would measure in our vector diagram. Okay. All right. So here again, step number 1, diagram. Okay. Step number 2, I'm actually going to put this down here. The velocity of B on that known length. Step number 3, these two kind of go together. It's going to be the vector diagram with its equation. And then step number 4 is really, in this case, finding that final value and measuring it off of our vector diagram. Okay. All right. So any questions right now, process-wise? Okay, so that was kind of sketching it out, not getting final answers yet. So let's look at some examples that are going to then illustrate how to do this in CAD. Okay, now, instead of, I was kind of, I don't know, thinking about this, instead of just doing random examples, we did a couple random examples, getting the process down. why don't we do maybe some of the homework problems that we have assigned, kind of get a start on that, okay? And seeing how those kind of work out. So let's take a peek at the homework that you have assigned for module 3. Module 3. So we'll kind of kill two birds with one stone. You'll get a little homework done, but then also practice on these types of problems. So I'm going to go back to module number 3 here and pull up assignment number 3. Wow, looks like there's a lot of problems there. Don't worry. Don't worry. That's why we'll do a couple of these here in class so you can get ahead of these. Starting with problem number 19. These are going to be the ones that are relative velocity. 12 and above are like general velocity ones. Okay. So the first ones are going to be kind of more related to the stuff that we did at the beginning of the chapter. And then the last ones, 19 and later, are going to be this relative velocity. So let's look at problem number 19 in your book. Okay. And you'll find problem 19 at the end of the chapter. Now, if you're looking at the chapter and seeing that we're skipping quite a bit, you're right, because we are focusing just on the graphical method for relative velocities. As you look at the other sections in the book, there are other ways of doing the very same thing that we're doing. It's just multiple approaches, okay? So, so we're picking one and going with it rather than learning all of them. So, so if we go to page 162 in your book, you will find problem number 619 right at the top. Okay. So problem 619 should look pretty familiar. This is a compressor linkage. Okay. And you'll notice that it has a 2-inch crank. Here's the crank over here. Here's the connecting rod, and here is the piston. In, what was it? Chapter 4. You guys set up this linkage already once for us, okay? Another problem that we're doing is going to be the reciprocating saw. You guys saw this one as well in that very same chapter. So if you go back to chapter 4, you probably have the base diagrams of these, okay? And you have to search a little bit. And then the other one that's going to be familiar to us is going to be this one right here, the shear mechanism. So these first 3 that we're looking at are going to be familiar, you know. I can't confirm if they're exactly the same, but I'm pretty sure they're pretty darn close if they're not the same. Bless you. So I have 19 already drawn for us in CAD. So if we go here, wait a second. Yeah, here's 19. Okay, so 19 is going to look like this in AutoCAD. All right. Bless you. And if we go back to the problem, it says for this compressor linkage shown, use the relative velocity method to graphically determine the linear velocity of the piston as the crank rotates clockwise at 1150 RPM. So clockwise is this way. So this is going to be our W2, if you would, and it's going 1150 RPMs, right? 1150 RPMs. Okay. Now I'm calling it W2 because when I look at my kinematic diagram, it's our classic 4-bar mechanism with our number 1 being the frame, number 2 being that crank, number 3 being the connecting rod, and number 4 being the slider. Okay. And then our A, B, and C respectively for each one of those links at the joints. Okay. So step number 1 is going to be the diagram. All right. The diagram. So make sure that you draw this to scale with all of the labels to start off with. Okay. I know sometimes students are like, oh, maybe we don't have to worry about the labels anymore. We're in chapter 6 now. We're going to continue to labels because our velocities are going to relate back to the points, and any angular velocities are going to relate back to the links. So we have to know which links correspond to what values. Okay. All right. So now what we're going to do is, as we look back at our process, the next thing that we're going to do is we're going to add in the lines of action of each one of the velocities that we're going to need to find. So if we need to find the velocity of C out here, this is just like the problem that we just got done doing in like a process or a sketch mode. And we'll notice that we added the lines of actions of each one of those velocities right on our diagram so that we would use the diagram then to determine our perpendicularities. So I'm going to go back to AutoCAD. And I'm first going to, I'm going to change maybe to 0 is fine. I'm going to change my, I'm going to add my line of action for C first, and I'm just going to draw a line. So it's going to go through that point and it's going to be horizontal. All right. I'm not going to add any arrowheads here. It's just the line of action for velocity of C, which is going to be horizontal. Okay. So just added a horizontal line through point C here. Then what I'm going to do is I'm going to add another line perpendicular to link number 3, which is going to represent the velocity of C relative to be its line of action. So line, I'm going to add, I'm going to start out here. I'm going to turn off my ortho. And then I'm going to go shift right mouse button, and I'm going to go perpendicular. These are all my object snaps that show up. And I'm going to go perpendicular to that link. So now I've got a line of action for my velocity of C relative to B, perpendicular to link number 3, or the line connecting B to C. And then my last one that I'm going to do is going to be a line. I'm going to start out here, and it's going to be perpendicular to link number 2. Okay. And that's going to represent, and I'm going to, oopsie, and then I'm going to move it to the endpoint there. And that's going to represent point B going up, let's see, up and to the right, because the rotation of this is going to be clockwise. So we could put a clockwise rotation on here. Do I want to do an angle or not? And I didn't want to get so, didn't want to waste time with this. Sorry. Now it's here. May as well finish it up. Let's see. All right, and then I'll put my lines on here that this is rotating in a clockwise direction. And I'm just going to show it like that. All right. So now I've got my lines of action of each one of my vectors on my vector diagram. Okay. And oopsie. When I look underneath here, since I have 1, 2, 3, and 4, and I have my A, B's, and C's, I want to now write my equation that is going to relate to the points that I have. So looking back over here, what we want to do is we want to write the vector equation so that we can solve for VC. And if we go back underneath here, our vector equation is going to be our unknown value, which is VC, which is going to be on our slider. It's going to be equal to our known value, the velocity of B, plus vectorially C relative to B. Okay. Now, as we look at each one of these vectors, we want to identify if we know magnitude and or direction. Okay. So for my velocity of C, and I'll kind of toggle back and forth here. I know direction, right? But I don't know its magnitude. That's going to be something that I'm going to need to find. So I'm going to go back underneath here, and I'll say, I don't know my magnitude, but I do know the direction, right? Line of action. And it's going to be along that horizontal line. Okay. My velocity at B. My velocity at B, I also know line of action. Okay, I know that it's going to be perpendicular here, but because I know the angular velocity of that link and I know how long that link is, I can calculate its magnitude. So I'm going to put a check mark for magnitude. I'll need to calculate it, but I know I can get it based on the information on the crank. And I also know its line of action. So this one, even though I have to do the calculation for the magnitude, I will be able to calculate both, or I will have both, right? And then the velocity of C relative to B, that one also is magnitude, is unknown, but I do know its line of action or its direction. So if I go back here, that's going to be perpendicular to link number 3. Link number 3. All right. Now, I'm going to do my vector equation. So I'm going to start with my equal sign. This is going to be my origin, right? That's going to be my origin to start off with. And then what I'm going to do is I'm going to draw link B, or I'm sorry, velocity of B to its length at the angle that it's at. Then through the endpoint of VB, I'm going to draw a line perpendicular to link number 3, which is going to represent C relative to B. And then I'm going to draw a horizontal line through the origin representing the line of action for C. And this is going to be my velocity of C. And then as we can see where those two come together, we'll be able to determine the magnitude of velocity of C. Okay. So in CAD now, we want to create this diagram. Okay. Because we want it to be nice and accurate and we can measure the value. So what we're going to do is we're going to go to AutoCAD. I'm going to move this up, maybe come in just a little bit. Okay. And I'm first going to start with an origin. So make sure you identify a crosshairs of some sort for an origin. Do my ortho. And we're going to go horizontally here. Now, my first vector is going to be vector B. All right. And back over here, we said we know the magnitude and a direction, but we actually need to calculate the magnitude. All right. How am I going to calculate the magnitude of the velocity of B? So if I go back to my original problem, I know that this is a 2-inch radius, right? And I know that this is rotating in a clockwise direction at 1150 RPMs. So how am I going to calculate the velocity of B? Yes, W2 in this case times R2. So my W2 in my problem is 1150 RPM. So I need to convert that, right? I need to convert that. So over here, I'm going to say 1150 revolutions per minute. Okay. And I need to convert that to radians per second. So 1 revolution, 2 pi radians. And then 1 minute on top, 60 seconds on the bottom. So minutes, revolutions cancel. We're left with radians per second. So W2 you get 120.42. Yeah. Okay. 120.42. So that means that that's going to be our value, 120.42 radians per second. Okay. Times the radius. Okay. The radius of that link was 2 inches, right? 2 inches. So we're going to multiply that by 2 inches. So our velocity at B is going to be, looks like 240.84 inches per second, right? Inches per second. That's the magnitude of velocity B. That's the magnitude of velocity B. Now you'll have to show these calculations so that you can, I can see how you got those values, but that's what we're going to use now for the length of that vector velocity B. Okay. So if we go back to AutoCAD, from that origin here along that line, we are going to draw a vector that is 240 units long. Now, this is only 2 inches long right here. If I draw a vector that's 240 inches long or units long, it's going to be like super huge on here, right? And I want to kind of maybe take a screenshot so that I see both my diagram and my vector diagram, my kinematic diagram and my vector diagram in the same snapshot. Okay. So since our number is 240, what I'm going to do is instead of using 240, I'm going to divide that number by 100 or move the decimal places over 2 places. And I'm going to actually draw the length of my vector 2.4084. Okay. So I am going to move my line. Move. Okay. I'm going to start at that endpoint. I'm going to put it down at the intersection right here. Okay. And now what I'm going to do is I'm going to draw a circle with a radius that is going to be equal to 2.4084. So it was 240.84, but I'm drawing it divided by 100, 2 inches, 2.4 inches, if you would, long. So now I'm going to extend this to that radius, and now it is the right length and at the right angle. Okay. I'm going to add my arrowheads. Remember, I can add them in the simplified form. We don't need to use liters. Okay. And I'm going to call this, I'm just going to copy this over here. And we're going to change that to VB. That's it. Okay. I've got it labeled VB and I've got it the right length at the right angle. So this line was the perpendicular line. I simply moved it down and I made it the right length so that it is exactly, in this case, 2.4084, okay, inches long. Any questions about that? So now what I'm going to do is on the end point of VB, I'm going to take this line right here and I'm going to move it. And I'm going to start with nearest, like right about there-ish, and then I'm going to put it on its end point right there. And this one is going to be called, I'm just going to copy my VB over and I'm going to call it, see, double click on it. It's going to be VC relative to B because it's C with reference to the known value of B. So it's C/B. And then now I'm going to take the line of action of C. I'm going to move it from that endpoint. I'm going to put it at the origin and you'll notice where my intersection occurs here. Okay. Now I could trim off those ends so I can hit the trim function. So trim this off, and that off. And then I can add my arrowheads for each one. So if this is VB plus vectorially C relative to B, then my arrowhead has to be here and here. Okay. And then VC goes back to the origin and its arrowhead is going to be at the endpoint of where that VC relative to B is. So that's going to be here. And then I need to label that vector down here. And this is velocity of C. Okay. Now, the important thing is, now the reason I need to have my labels here is when I do my vector diagram, if I have things called VB, I want to be able to look up in the diagram and see where B is. Okay, like that's the velocity of point B, and that I can relate that vector then to that point. The same thing here, velocity of C. If I have a C down here on my vector diagram, I better see a C up here in my kinematic diagram, because that's going to be the velocity of point C, which is the joint or the center of this slider. Okay. And then C relative to B is going to be the line connecting those two. Okay. So now the one that I'm interested in is what is the magnitude of the velocity on point C, which is that slider. So I am simply going to, I'm going to go on my notes layer and I'm going to add a linear dimension here to this value. Okay. Now, your velocity of point C is not 1.76 here. What is it actually? Exactly, 176.57 inches per second. That is the velocity. So make sure that some way, somehow you let me know that that's the actual velocity. Don't just leave this here and be like, okay, I'm done. Okay. Make sure that you're answering the question. The velocity of the slider is 176 0.57 directed to the right horizontally or something like that. Okay. Now the work that you need to show, you need to send me, I want everybody's attention right now because I know you're trying to get the problem done. I get it, but I want to make sure that you know what to hand in. At this point, when you scale this, okay, you can take the screenshot of this then, okay? So this would be, well, I use Windows Shift S. You can use the snipping tool or whatever. You would have this. This would be part of what you would be handing in. That is not all you'll be handing in because I also need to see the calculations for your velocity of B and any of these values that you needed to do the conversions for, okay? And then also your final answer, probably saying, you know, VC is equal to 100 and did we say 70? I forget it. 176.57 inches per second. And that's your final answer then from your vector diagram, okay? Now, this can be done underneath my camera. This can be done by hand in a neat form that I can read it, okay? And then the screenshot would accompany it so that I would know where those values are and where they're, you know, how things are related. Some students like to put all the work on AutoCAD. If you want to do that, that's fine. I'm totally fine with that. But if this is easier, as long as I can read it and I can follow it, I'm okay with the manual calculations on a separate piece of paper as well, okay? So any questions about what to hand in?
You want the kinematic drawings to have dimensions on them?
No, I think it's going to get too cluttered. I'm going to trust that you have it and I'll know by the final answer. Now, when you look back at your assignment, okay, when you look back at your assignment, there is an answer key here, okay? So when you look at the answer key, I give you just the final answers, except for these. So when you start looking at the velocity of, or I'm sorry, problem number 19 that we just did, notice that I give you the velocity of point B, 240.855 inches per second, okay? That's really not a final answer. It's an intermediate answer so that you know that you're on the right track, because if you don't get VB right, the magnitude, then your other part isn't going to come out right. So this is not a final answer. This is kind of an intermediate. So by the time you get to the final answer, which is what the problem is actually asking for, that you have what you need. There's just so many steps here. I want to make sure that you have at least, if you don't get VB, you're going to be like, at least you stop there and you haven't gone through the whole problem and are like, oh crap, I didn't get that final answer. Okay. So some of these, like I said, the VBs are intermediates for you before the final answer. So just so that you know you're on the right track. Okay. All right. So right now, process-wise or even handing in wise, any questions at all on problem number 619? I use the diagram to get their direction, but then I move them to the vector diagram and then either trimmed or extended those values to be the right value or the actual number if I knew it. So for VB, I extended it on that radius. And then for C relative to B and C, I just trim them off and I just have them down there. Yeah. But I needed this vector diagram to get the direction. So I could do like perpendiculars or inlined with and stuff like that. Okay. And using CAD is really the best way to go because it is the most accurate, especially for getting, you know, the angles right and things like that. All right. Okay. So that's a crank slider mechanism. All right. Let's do another problem. All right. And this one is going to be number 27. Number 27. Now, what I'm going to do is I'm going to give you a chance to get this started. Okay. So I'm going to pause the video for a little bit and I'm going to have you guys draw the kinematic diagram here in AutoCAD. And then once everybody is kind of like there, we'll go to the next step and we'll kind of get started on the problem. So, oh shoots, that's not the one I wanted. I'm so sorry. I'm so sorry. Don't look at that diagram. That's the wrong one. That's an example. I need 27. This is the one. This is the one. Sorry. It's this one. This one. Okay, so I'm going to kind of go underneath here first. I'll introduce this problem and then I'll let you guys, get the kinematic diagram going. So on page 163 right here, this is the diagram for number 27. This is a device of a sloshing bath used to watch vegetable produce inside of this, water bath here. For the configuration shown, use the relative velocity method to graphically determine the angular velocity of the water bath, okay, as the crank is driven counterclockwise at 100 RPMs. So this is going to go in this direction. Here's the crank. Okay, here's the connecting rod. And then this link right here is the bath. And we want to know what is going to be, the direction and the angular velocity of this kind of sloshing back and forth. Okay. All right. So the kinematic diagram using the values that are here. Okay. So using the dimensions, the kinematic diagram in its simplified form will look like this. Okay. So I'm going to pause the video right now, take time to get this drawn up, and then we'll continue on from here and we'll kind of do this one together. Oopsie. Sorry. What the heck? Got it? Yeah. I don't know what happened to my, I've got this thing. I hit the annotate in Zoom. Let me pull Zoom back up. Come on. Okay, so now that we have our diagram done, let's look back at kind of our process to see kind of where we're going. So diagram done. Okay, you have all of your labels on, the links, the joints, all that kind of stuff, and everything drawn to scale. Then what we're going to do is we're going to kind of go ahead here and we're going to see, we've got to find out what is the velocity, the angular velocity of link number 4. Okay. Angular velocity of link number 4. Now, to get the angular velocity of link number 4, what's the equation that I'm going to use? So W4 would be equal to, do you remember? Yes, it's going to be V over R, because our base equation is velocity is equal to W times R, right? So it's just algebraically rearranging it. And now we're going to have V over R. So now if we look back at our kinematic diagram, okay, here's link number 4, and we want to know its angular velocity. So if we need to know its angular velocity, we have to know the velocity of a point along this link, velocity is C, right? In order to get its angular velocity, because we also know its length. Okay, so that means I need to get the velocity of C. Okay, so if I go back underneath here, my vector equation, which is going to be familiar, we've been kind of revisiting this very same equation for a 4-bar mechanism, is going to be the velocity of C is going to be equal to the velocity of B, because B is on the crank where we know all the information, plus vectorially the velocity of C relative to B. Okay, now just like all the other processes that we looked at, we can, or we know some information about each one of these values. We don't know the magnitude of the velocity of C, but we do know its direction. And we know its direction is going to be perpendicular to link number 4. Okay, and we'll put that in just a little bit. Then we're going to go on to velocity of B. We can calculate the velocity of B because we know how fast, or the direction and the value for which the link number 2 or the crank is going around, and we know how long that crank is. So we can calculate the magnitude and we know its direction, perpendicular back to its radius of rotation. And then the velocity of C relative to B, we don't know its magnitude, but we know it's going to be perpendicular to the line connecting C to B. Okay. So our job right now, before we can really go and do anything in our vector equation, we need to calculate the magnitude of the velocity of B. The magnitude of the velocity of B is going to be W2 times R2. So if we go back to our problem here, our problem says that our crank is rotating counterclockwise at 100 RPMs. Okay, and the length of that crank is 80 millimeters. So we know R to be 80 millimeters, and we have to calculate W2 100 revolutions per minute. We need to convert that to radians per second. Okay, so we're going to go ahead and do that. Revolutions cancel top to bottom here. And then we're going to get our minutes. 1 minute is equal to 60 seconds. So minutes cancel here. So our W2 then in radians per second, multiply across the top, divide by the bottom. .4 radians per second, or I'm sorry, 10.47 radians per second. So that's the number we put right in here. So our VB is going to be 10.47 radians per second times 80 millimeters this time, right? That's the length of that crank. So our magnitude of the velocity at B, it's going to be 837.7 millimeters per second. Okay. Do you guys get that same number, hopefully? So the 10.47 times 80. Yeah. Now, this is the magnitude of the velocity at B. So that's where we got our magnitude from, right there. Okay. Now we're ready to look at directions. That's the only magnitude we can get. Okay. The other ones are going to be off of our vector diagram. Okay. So now we're going to get directions. So we're going to go back to AutoCAD and the diagram that we created. So the key to velocities, we know when we're looking at most velocities, except for translational motion or like a slider, we know that the velocity has to be perpendicular to the radius back to the center of rotation. So for velocity B, okay, for velocity B, this is going in a counterclockwise direction. So it's rotating this way, okay, rotating that way. So that means the velocity of B is going to be perpendicular to this length going up and to the left. Do you see that? Okay, so I'm gonna move my link number 2 right here. Okay, and I'm gonna draw a line, and that line is gonna come out from random, and it's gonna be perpendicular to link number 2 right there. And then I'm gonna move it to the endpoint right there. So right through point B, the velocity of point B is gonna be going perpendicular 90 degrees to link number 2, and it's gonna be going in that direction. Okay, I'm not going to put the arrowhead on right now because I'm going to have to draw it to its correct length. Okay, and that'll happen in a little bit, but that's its line of action. Okay, everybody see how I did that? So I did a line away from the link, shift right mouse button perpendicular to that link right there. Okay, and then I could move it from that endpoint to where I wanted it to be. Okay, so that's how we get that perpendicular. Now I want to do that very same thing for link number 3. I want to show the line of action of the velocity of C relative to B, which will be perpendicular to the line connecting C to B. The line connecting C to B. So here again, line, perpendicular, and I'm going to start at a random place, shift right mouse button, perpendicular to. So that's the line of action of V relative to C. I'm sorry, the VC relative to B. And then lastly, the velocity of C. Now, if the velocity of the rotational velocity of link number 2 is going in a clockwise direction, counterclockwise direction, so it's going this way, then which way do you think the angular velocity or the rotation of link number 4 is going to be, clockwise or counterclockwise? Counterclockwise as well, right? If that's the case, counterclockwise this way, then the velocity of C needs to be up and to the left, perpendicular to link number 4. Agreed? Okay. So that is going to be from here, perpendicular. And then I'm going to move this to the endpoint here. Okay. So now I've got my directions for each one of my velocities. Okay. Now let's go back over here. Our velocity of B was 837 millimeters. Okay. And if I look here, how long? Oh, it's 800. That's not terrible. I think we can draw this 1-to-1. So if this velocity VB will be a little bit longer than the length of link number 3. So I think we can draw it 1-to-1 on this diagram. Okay. So I am going to start, I think I'm going to draw it like over here. Yeah. And I can always move it. So I'm going to start with an origin. Okay. Okay. And I'm going to then move my line that represents the line of action of velocity B, and I'm going to put it at the intersection right here. Okay. Now I'm on my first vector on the right-hand side of the equation, and I'm going to draw a circle that has a radius equal to 837.7 millimeters. So then I'm going to extend that line to the radius. Now my velocity of B, line of action, is the correct length. Okay, so if I delete this and I measure that length and a line dimension from here to here, and I look, that is 837.7 millimeters long. Okay. All right. So any questions about getting that to the right length? All right. And I might as well put my arrowheads on here right away and label this velocity of B. I'm going to take this and I'm going to put this over here and right in front do capital V B. Okay. So that's the velocity of B. That's the only label I have to put on there, as long as I have the right line of action and the right length. Okay, questions so far? Now on the endpoints or on the tip of the velocity of B, I am going to add the velocity of C relative to B. So I'm going to move this, okay, nearest, right about there, to that endpoint. Okay, and that's going to represent the velocity of C relative to B. Okay. Something like that. Okay. Now that's as far as I can go on the right-hand side of my equation. Okay. So I've done this so far. And that's all that I can do because I don't know how long the velocity of C relative to B is. Now I'm going to cross over that equal sign and I'm going to start drawing the velocity of C. And I'm going to try to find an intersection. Okay. So now my velocity of C is right here. So I'm going to move that. I'm going to start its endpoint at the origin. And now I need to find my intersection, and they're going to intersect up here, right? Now, what I can use, there's a function, fillet, in AutoCAD, but it has to have a radius of 0. Okay, so I'm going to click the fillet function, and then it'll actually find the intersection of the two and trim them as well. So where's fillet? Fillet's right there. And I'm going to check my radius, R, enter, and it's at 0. And I want it to be 0 so it makes a sharp corner rather than a radius. So I'm going to click on this one and that one, and it'll automatically find their intersection. And then I can trim away this right here. Okay. Now, arrowheads. So if this is V plus vectorially C relative to B, my arrowhead is going to go there and there for C relative to B. And then I need to copy this one and change this to the velocity of C. Okay. And its arrowhead is going to be at the endpoint of the end of the other side of the equation, right here. So its tail is going to start at the origin and its tip is going to go to that last arrowhead. Now, before we move on and do anything else, how's everybody doing? Any questions to this point? Okay, so as you see the labels here, this is what I'm expecting for the work that you hand in, okay? That you hand in. Just make sure that the labels are large enough so that I can read them, okay? Now, looking back underneath, okay? So I've done my vector equation, okay? I did my vector diagram. I now need to find magnitude of the velocity of C, right? The magnitude of the velocity of C. So to get that off of my vector diagram, I need to add a dimension. So I'm going to change this to the notes layer, and I'm going to do an align dimension from that endpoint down to there. Now, darn it, it's not big enough. So I need to go into annotate, dimension styles, modify, and on that fit tab, it's at 1 right now. I'm gonna go 10 for right now and set as current and close. Yep, that was good. Okay. So I want to be able to, I just have to have that dimension large enough so I can see it. And what I'm going to do is I'm going to move this diagram so that it's a little bit closer down here. And then when I take my screenshot, I have everything in there so that I can read it. Okay. Now, this is 815. And that's going to be millimeters per second. So instead of having to worry about units in your vector diagram here and adding them to the dimension and all that kind of stuff, you can simply, you can simply put in your, handwritten notes of the calculations that you do, you can simply put VC is equal to 815.11 millimeters per second, okay? You don't have to try to change the dimension to add the units or things like that on the CAD, okay? And now that I have the velocity of C, this is the value now that I'm going to be putting into the equation to solve for the angular velocity of link number 4, okay? So all I needed that vector diagram for was the velocity at C. Okay, so let's go ahead and put in our velocity at C here and calculate that angular velocity for link number 4. And then we've got to look, what is the radius of link number 4? That is 720 along here. And that's just millimeters. So you should get W4 equal to 1.132 radians per second, right? The millimeters canceled out here top to bottom, so it's nothing per second. Make sure when you show your calculations that you see the cancellation. So radians are going to come in, all right? Now, as a final answer, we don't want to leave the radians per second. We want to convert this to revolutions per minute, okay? So you're going to be converting it back. You're going to do 2 pi radians on the bottom here, 1 revolution, and then 60 seconds in 1 minute, right? Seconds, radians. So you have revolutions per minute. So our final W4 is going to be 10.81. And that's going to be RPMs. Now, besides the value the magnitude, it's units. You also need to know direction. And I believe we said it was going counterclockwise, right? And that would make sense. If we go back up to A, velocity of C is going up and to the left. So if we would put our finger at D and pull this up and to the left, it would go in a counterclockwise direction. Okay, so you want to add that direction as well to the final answer. So handing in wise, what you would do is you would take a screen snip around the outside here, and you would add it to a document, and then you would accompany it with your manual calculations that you did for VB, writing out the vector equation, and then calculating what your W4 is at the end. Okay. Any questions at all? Okay. So this one was a crank rocker. The 619 was a slider crank, okay? And then you're going to notice that the other ones that you have left are examples of each of those as well, okay? So, so I'm going to stop there with our lecture.